Hey folks, I'm Mark, and welcome to my office. Yeah, the shop is still a mess. But that's okay, because today, for today's episode, I actually need a computer. So this worked out. Today, I'm going to be putting together the electronics for the lighting sequence for Dr. Theo. Now, the main question I had is, what hardware do I actually need for that? Now, this initial version of Dr. Theo is going to simply drive the lighting sequence based on the voices that it hears in the room. So I definitely need a microphone of some sort. For that, I purchased the analog MEMS microphone breakout from SparkFun. Now, to actually drive the LEDs, I need something with some compute capabilities. So I looked at a few different pieces, and I settled on an Arduino Theo and the LumiDrive, what is it called exactly? The LumiDrive LED driver. And my initial thought was the Theo would have all the programming, the LumiDrive would allow me to access the lights, and then I could use the microphone as input. Now, the more I looked at the LumiDrive, though, it has the ability to do its own compute. So, I'm wondering if I can just get away with just the LumiDrive and the microphone and just hook the two of them straight together. So that's where we're going to start today. Now, I'll have links in the show notes for all of the components that you're going to see today, as well as links to all of the iterations of the script that I go through to try to get the lights to blink and turn on and off as I need them. So let's get started. First of all, I'm going to be using, for the lights themselves, I'm going to be using an LED strip. It's got 60 individually addressable LEDs. So I can actually program each one of these separately and with a separate color and so on. Which is important because what I'm going to do is to light up Dr. Theo, all of the LEDs around for his eyes, his eyebrows, his mouth, all around the body, all of that is going to be one string of LEDs. Just for convenience, I ended up just taking a long board and zip tying the LEDs to it just so I could keep it, otherwise it'll curl in on itself and it'll make it hard to see which LEDs are lighting up. Using a SparkFun LumiDrive for this as the main processor. This allows me to use CircuitPython, actually, which is my first experience with that, to program the individual LEDs. It's got a nice, right now I'm just powering it off of the USB-C, but it'll have actually, when it's in the Dr. Theo, it'll actually have its own power supply. I've got a little lithium-ion battery that plugs in there. The next bit was actually trying to make lights and everything blink the way they're supposed to blink. The SparkFun LumiDrive came with some sample code that got me started. When I ran the initial code, this was as fast as I could get it to blink. Which seems reasonable, but unfortunately that's actually much too slow for what Dr. Theo needs. Here, let me do it again so you can see it. So I started looking around, seeing if what I could do to make that faster. And one of the things, probably one of the first things I discovered was that the LumiDrive shipped with an older version of CircuitPython installed, version 4. The most recent one is version 8, 8.2, and some change. So I said, all right, well, let me start with that. Let me just start by upgrading that, just so at least I'm running on the most recent version. That sped things up immensely. Literally just upgrading CircuitPython using all the same code. Now, this is as fast as I could make this thing blink, and you almost can't see it. So let me walk you through the lighting sequence to show you how this is going to work. Let me turn all the lights on steady so that we can kind of walk through the strip and actually walk around his head. First things first, we're starting imagine just a picture of Dr. Theo's head. I'm starting with his mouth. So the first 4 are going to be for his mouth, and then there'll be a break. The next 3 will be his goatee, and then a break. This first one, all the whites are the lights that go around his head. This one is the right, what I'll call his right jowl, so lower right corner of his face. And then I'm going to skip 2, just because it's convenient, just to keep these off. And then this one will be his right cheek. Then here's his right eye, these 3 purple ones. His right eyebrow. And then there's 2, he's got 2 separate eyebrows. One of them I think has 7 LEDs, the other one has 8. So that's what this stack is. So somewhere in here there'll be a break, but mostly this is just a line of LEDs, and then the other eyebrow. Then his, well, I'll call his, I don't know, his right forehead. And then there's several ones that are turned off. These go over the top of his head. Then his left forehead light. And a couple of other blanks. And then his left eyebrow. His left eye. His left cheek. And his left jowl. And that takes you all the way around. And all these ones at the end will be trimmed off because they're just not needed. Now I'm going to end up having to break these in several places, break the LED strips, but thankfully the LED strips allow you to cut these right at these copper junctions, and then I can solder wires back on to connect the 2 halves, and that'll allow it to maintain a solid connection. I thought about trying to do this as just one long strip of LEDs and just doing, you know, tricks like this where if I don't need them I just keep them off. But there's too many like right angles or more extreme angles that I have to do turns and whatnot, and the LED strip just wouldn't play well. Or if it did, even if it maintained, you know, if I could actually make those turns, you would see a lot more of the LED strip. Alright, the scripts for everything I'm about to show you follow the same basic pattern. The first part imports a series of libraries that we need. One of the most important ones is the Adafruit .star library. That'll be the one that we actually use to get a hold of individual pixels on the strip. We define the number of pixels that are on our strip and how bright we want them to appear. I've got this dialed way back because this is just totally bright enough for what we need to do. And if I don't turn up the brightness to the full, the LEDs will last longer. Then I get a reference to the Adafruit .star library itself, and pixels ends up being an array of 60 elements. So now I can say pixel sub 0, pixel sub 1, and so on. And what I can do with that is I can set it to a series, 1 or more colors. Now this list this was actually the default list that came with the LumiDrive. So I just left them in place because all the colors that are here work for my purposes. But as you can see, it's just an RGB color scheme, so you can define whatever you need to in that range. There was also a predefined function called color fill, which will fill the entire strip with the same color, and that's useful. That's very handy when I actually want to turn everything off, because that happens to be black. Black is turning the LED off, so I can fill the entire, if I want to reset the whole strip, I can just say color fill black and it'll turn everything off so I can start over fresh. The one that I just showed you was showing all of the individual pieces all on, just so you could see where they fell on the strip. And that's what this function is doing, and it's quite straightforward. It's just starting at pixel 0, the very first one on the board, and saying, alright, the first 4 are red, and that's going to be what I'm calling the mouth. The next 3 are the soul patch, and those are also red. Then there's the right cheek, and that's a white one, 2 black ones, and then another white one. And so on down, just going all the way around the face. And at the very end, I can just call that function and turn this back on. Run the actual program to turn all these on. This is the SparkFun analog MEMS microphone breakout. So the microphone, the actual mic is there. For this first iteration, the first thing I did, you'll notice that this is the board is now actually, the LumiDrive is actually now on a breadboard. I've actually soldered headers to all of the breakout pins, so I can just drop it right onto the board. Then what I did was I ended up taking some of these hookup wires, 3 of them, and just kind of snipped off the ends and then soldered them onto the microphone. The red is the voltage in, and that's connected, that voltage into the mic, and that's connected to the 3.3 voltage output of the LumiDrive. The black is the ground, and then the yellow is the data line, and that's hooked up to the analog 4 pin of the LumiDrive, the A4 pin. But what does the mic actually output on its data line? Well, what it outputs is a voltage. Now, to get an idea of what this looks like, the first thing I did was I just hooked up a couple of other pins to a couple of other hookup wires to the analog line and the ground line of the microphone. So basically I'm sampling what's coming off of this mic. Then what I did, was I hooked up my multimeter. So let's move this back so you can see this. The voltage in to the analog line and then the grounds together. So now what my multimeter is going to show is how much voltage the microphone is actually reading once I plug it back in. When it's quiet, the voltage reads 1.598, something like that. If that's the quiet state, then anything above that, as the noise level gets louder and louder, I would expect the volts to go up on that analog pin. I could translate that voltage into some number of pixels. As the mic reads louder and louder noise, it would light up more pixels, and basically build myself, out of this LED strip, build myself a a volume meter. So that's what I'm going to show you first. All right. So, in order to get the data off of the microphone and translate it into some number of pixels to light up, the first thing I do is I import a new library called Analog.io, and then I create a microphone in variable that reads the value coming off of the board's A4 pin. So that's the pin that's hooked up to the microphone's analog line. So first thing I need to do was figure out how do I get the voltage off this pin, or translate, or more correctly, translate the value I get from the pin into some voltage. And what I do for that is I wrote a very small function that takes the pin value, multiplies it by 3.3, because that's our maximum voltage for this pin. And when I used just that by itself, I was finding that the values anyway, were just maxing out the rest of my function. So through some trial and error, I kept dividing it by some number, several numbers, until I got to one that made it a reasonable value to work with. And in this case, it just happened to be 2 to the 16. I started small and then just kept cranking it up until I started getting reasonable values. So this function, getVoltage, does just that. It takes the value off the pin and returns a value that is a voltage, something between about 1.5 and 3.3. The next thing I did was I created a function that takes that voltage and converts it to some number of pixels. So I take the raw voltage being passed in, I subtract off the 1.59, because that's at quiet, that's what seems to be the base value for the microphone. So let's just get that out of the mix, and then what's left I multiply by 100. So effectively what I'm doing is I'm amplifying the differences that happen in the second and third decimal places of the pin's value. I convert that to an int, and that I'm calling that the number of pixels to light up. So then I just have a very simple for loop that says for the pixels in that range, turn them on and make them red. And then finally, I wrote a new loop that resets it to black, so it turns everything off first, and then it calls my two functions to get the value off the pin and turn on that number of LEDs. So as fast as this loop can execute, it's going to be sampling the audio environment and turning that into the number of pixels to light up on the board. So here's the board, the mic translating what it hears to some number of pixels. Now I'm talking kind of softly because what I discovered, if I make too large of a noise like this, then the lights just get stuck. They don't actually reset. So what that called for was a minor modification to the code. Okay, so the minor tweak that I had to make was with the convert voltage to pixels function. Previously, I was just subtracting off the 1.59 and multiplying it by 100 to amplify the differences as it read the voltage. But I believe what's happening is when it gets a really loud sound, or even a moderately loud sound, this just goes to effectively infinity, and it just gets stuck there. So I modified it to take the minimum of either the value that it's getting off of the microphone or 59. So whichever one of those is smaller, that's what it's going to use to that's the number of pixels that it's going to use to turn on. So if it tries to go off the edge of the scale, it's going to basically cap it at 59. Here's the revised script, the one that I'm calling with guardrails. And as you can see, as long as now that that guardrail is in place, I can talk as loud as I can want. I can make all the music, or I can make all of the sounds that I want, and it spikes, but it doesn't actually ever get stuck. It just goes up to the maximum, the 60 pixels, and then stops there. So now I've got a reliable way to read the volume, effectively the volume coming off the microphone. Today, I'm going to build the main script, the actual script that's going to be used to control Theo's lights as he's speaking. We've already got all the pieces put together in other scripts, so I'm just going to basically hobble something together, and then we'll start tweaking it to make it closer to what we see in the show. I'm starting with a script, one of the volume meter scripts, and we definitely need to be able to get the voltage off the pin. We need the core of this function. We're not going to be converting the voltage to pixels anymore, but we do need to be able to get the voltage off and then trigger the lights based on how high the voltage is. So we're going to start with this line, and I'm going to create a new function called isSpeaking. And we don't need the minimum. We don't need to cap it at 59 anymore. What I'm going to do is I'm just going to start by saying if that is greater than 10, we'll just start there, and like I said, we can tweak this later. Now the raw voltage is actually passed in as a parameter to this today, and that's the value of the return value of get voltage. So what I'm going to do is I'm just going to kind of cheat and say, well, I'll just call that directly right from isSpeaking. And that way I can get rid of this entire function. So now, in my while loop, what I want to do is I want to say, if isSpeaking returns true, then I want to go into the speaking loop. And if it's not, I just want to say stop speaking. Now both of those functions actually, those were ones that we defined for the blinking, one of the blinking tests. So I'm going to come back over here, and I'm just going to copy these two functions out. This one's stop speaking, and then here's speak. We'll just copy both of those and drop them in here. And then we're going to say, for now, I'm just going to comment these guys out. Actually, I do it this way because it's a little bit easier. And in my main while loop, I'm going to say if is speaking. Then I want to call the speak function, and I'll say pause for 1/100 of a second, and then say stop speaking, and pause again. Otherwise, I just want to stop speaking. Just that's the resting state. So let's start here. We'll see where we get with this. This is a test. This is a test of speaking. Hello, 1, 2, 3. It's definitely triggering. But it's the blink is way too fast. So 1/100 of a second, not nearly long enough. So let's crank this up to 5/100 of a second. Again, we're just trying stuff here, see how it looks. This is a test of speaking. This is version 2. I think I want the speaking loop to stay on for a little bit longer. So I'm going to say we're going to bump that up to 1/10 of a second. See if that gives a better effect. Hello, this is your Buck Rogers. Test, test. That's better, but I think we've now we've overshot. So I'm going to back this out to 0.08. This is a test of speaking. This is version 3. Version 3. So that's really it. We can get rid of that just to clean it up a little bit, but there's our main loop. Not too bad. So in the next episode, I'll be breaking up the LED strip into the various sections, like each eye and his cheeks and his eyebrows and things like that. And then the real fun begins, which is trying to figure out how to mount all of those LEDs inside of Dr. Theo and minimize how many of the wires you see from the outside. So, talk to you later. I've got a syntax error somewhere. What I found was if I make a relatively or even moderately loud noise, so let's just try commenting even more out. Like this.